Hello, welcome back. This is Calculus by Dr. Oz. Today, we're going to go over an exercise where we're going to talk about parametric equations. We have three sets provided to us, different from the classical representation of the curves or classical equations of the curves. We also call them rectangular equations. In the parametric equations, we have a parameter that sort of like defines the x and y coordinates of the points on the curve. And this parameter is particularly important in space applications because when you send a satellite to the space, it follows a specific trajectory, and t generally becomes the time parameter. So that tells you how fast the satellite or rocket is on its trajectory. So you cannot talk about speed of the satellite or speed of the rocket without using parametric equations or y equals f of x type representations of curves. So, and different from the rectangular equation case, when you graph the curve, you have an orientation, so it tells you in which direction you go from point A to point B. So that's also another difference. So first of all, why don't you get ready with your calculator and make sure you know how to graph parametric equations. But also, we're going to learn, obviously, in this exercise, that how do you convert parametric form to the rectangular equation form. So we're going to also talk about that. I don't want to give you more heads up, but all I can tell you is that we have really nice graphs. As you see that you have directions provided to us, like in the first case, is the parabola. So we have the direction prescribed. In the second case, we have a hyperbola. As you see, we also have direction on the hyperbola. And also, we have an ellipse in the last case that you see that direction goes counterclockwise. So I don't want to give you more heads up because we're going to obtain each of them within the video. So I think it's better to get started now. All right, let's start with part A. We have the parametric equations provided to us with the parameter t. Okay, so x coordinate is a function of t, so it's t squared plus t, and same as y coordinate, but it's a different function, t squared minus t. Okay, so what we're going to do next is to be able to get a plot of the curve. We're going to choose some sample points for t, and we're going to get the x and y coordinates of those points, and then we're going to have those points located on the xy plane. And all we're going to do is just keeping the, obviously, direction starting from t equals, just making it up, 0 to t equals 5. We're going to just connect those points by a continuous curve, and that's how we're going to get the curve of the parametric equation. So you can go ahead and use the use your TI-84 to graph it, but I think at this moment doing this by hand helps you to see like why the curve looks like the way it is. Okay, so I did that. I also did that with some choices of sample points. So as you see that I chose points starting from, for t obviously, t is the parameter, starting from -5, going all the way to 5 with the increment 1. Okay, so I got x and y coordinates of the points as I substitute these t values back into the description of x and y. Okay, so for example, for t equals -5, x of -5 is -5 quantity squared plus -5. That takes you all the way to 20. And if you plug in -5 here for y, then it's -5 squared minus 5, that is 30. So I got the first point on the xy plane, which is 20 and 30. So let me just like have a bigger circle to represent that point. I have more points, in fact, listed on the graph, but in total I have only 10 sample points. And the next t value in the list is -4. And if you plug in -4 for x and y, you get the x coordinate 12 and y coordinate 20. That takes me to this point here. And next is t equals -3. that spits out the point to be like 6 and 12. Here we go. 6 and 12 is right here. Okay. So as I said that we have a direction in the graphs of parametric equations. And I started here going in this direction, right? So that I have to keep that direction as I move along the curve. Obviously, uh, this is already connected. Like the points are already connected by a continuous curve. But at the end, what we're going to do here is that we're going to sort of like have like a nice continuous curve to connect those dots. After you're done plotting those points and keeping the direction with that. Okay, so let's choose some other sample points to see where we're going to end up. So let's say like t equals 0 takes you to the origin. So that means the curve is going to pass through the origin. Okay. For t equals 3, I have 12 and 6, right? 12 and 6 is right here. Okay. And then let's look at the last point, t equals 5. That takes you to the point 30 and 20. So that's where you end up with. Okay. And as I said, eventually you just connect all the dots by a continuous curve. And as you see that this is like a very nice curve following this direction here. Okay, so you have to keep the direction on the curve. All right, I think that's so like the description of like how we plot parametric curves. And in the next part of the question, we were asked to go back to the rectangular equation. In other words, we want to have the actual x and y representation of the curve. So we need to have the form written as like y equals f of x without any parameter. Okay. So in other words, we're trying to eliminate the parameter. So let's just do that. To eliminate that, this is an algebraic question, essentially. How do you solve this equation for t? So, in fact, these equations for t, because we have two of them. X equals t squared plus t, and y equals t squared minus t. Well, what we can do here is that we can subtract the second equation from the first equation so that we can eliminate t squared. So on the left, I have x minus t. On the right, I have t squared minus t squared, which is 0, and t minus minus t, okay, which is in fact 2t. Okay, this implies that t is in fact x minus y over 2. So once t is written in terms of x minus y over 2, we can go back and plug this back into the equations. And for this purpose, I'm going to use the y equation, obviously, because I want to have the representation of the curve written as y equals f of x, right? Or maybe implicit representation, but either version is fine. You can also choose to start with like x equals t squared plus t if you want to. Either one is fine. So y is equal to t squared, which is x minus y squared over 4. That's the quantity square of t, right? Minus x minus y over 2. Okay? So here we go. So let's just simplify this. X squared minus 2xy plus y squared equals 4 minus x minus y over 2. Okay? And I don't need this part anymore, so I can get rid of that. And all I'm going to do is to find a common denominator. Okay, so let me just keep this here. Okay, and the common denominator is 4, so I should multiply the second fraction, like the top and the bottom, by 2, so that y is x squared minus 2xy plus y squared minus 2x minus y divided by 4. Okay. Right. So 4y multiplying both sides by 4. 4y is equal to x squared minus 2xy plus y squared minus 2x plus 2y. and subtracting 4y for both sides, okay, takes you to x squared minus 2xy plus y squared, let's see, minus 2x minus 2y equals 0. Okay, this is sort of like the full representation of uh, uh, the graph. This is the full equation. Go ahead and check if this is a parabola or if this is a hyperbola, ellipse, circle, depending on the properties of this full form, quadratic form, both in x and y. All right, I think we're done. One final comment here, since this is the very first exercise of this section. The graph of the curve parametrized by t does not define a function. That's why we need to parameterize the equations, because again, if you were supposed to graph this with the xy representation or rectangular equation form, then you wouldn't be able to say that the xy representation defines a function. And this is the xy representation. This doesn't define a function because it doesn't satisfy the vertical line test, right? So the graph doesn't satisfy the vertical line test because it crosses, any vertical line crosses the graph at more than one location. So this doesn't define, the graph doesn't define a function. But this way, we can still work with all nice properties of this converted parabola. I also wanted to zoom in here just for you to convince yourself that the curve crosses the y-axis and makes a turn and crossing the origin, and then makes another makes that turn fully, and then crosses the x-axis and going all the way in its direction. So I just wanted to zoom in for you guys to see better. Okay. All right, let's move on to part B, but in the next video, please move on to my next video to see what I'm going to do for part B.